Welcome back everyone, Patrick here, moving on to the next question. This is a pretty cool one, dealing with quadratic relations. So we are given the first four diagrams of a pattern over here. So diagram 1, diagram 2, 3, 4, etc., and the pattern would continue indefinitely. And then given that pattern right there, what we have to do is we have to make a table comparing the base length of each of these diagrams. So notice this one here, it has a base length of 1 unit, right? This one has a base length of 2 units, 3 units, 4 units. And then the area of each of those would just be the sum of the squares, right? So this one has an area of like 2, this one has an area of 5, this one has an area of 10, etc., etc. So we got to make a table comparing both of those, and then we have to figure out what kind of relation we're dealing with. So we're going to use finite differences to determine whether you're dealing with a linear, quadratic, or neither. And then in part B, we have to find an equation comparing the base length to the area. So actually have an equation that relates both of them, not just a table. And then we have to describe the transformations in that equation that are done on the base function y equals x squared. So notice that kind of in part B, we almost answer part A. Okay, we can expect to be dealing with a quadratic, but we still have to show the work. You wouldn't just get full marks right there. Okay, so let's go through this. So let's make this table over here. So again, we're going to compare the base length of each of these to the area. Okay, so starting with this first diagram, if we have a base length of 1, notice that we're not told whether this is like 1 centimeter, 1 meter, so we'll just keep it in abstract form, just in general, just 1 unit. So I'm just going to put a 1 over here. What's the area going to be? Well, it's going to be the sum of the squares, which is 2. Another way to look at it is length times the width. Notice the length has a length of 1 unit, and then the width has a length of 2 units. So 1 times 2 gives us 2, right? Or another way is you could just sum the squares. Over here in the second diagram, notice the base length, 2 units. What's the area? Well, it's going to be 1, 2, 3, 4, 5, right? It's going to be 5 of those squares, right? You can't do 2 times 3 because there's 1 unit here missing, right? So you can take the area of like this rectangle, which would be 1 times 3, right? This is 3. And then you could take the area of this rectangle, which would be 1 times 2. So this would have an area of 2. This would have an area of 3. 3 plus 2 gives us 5, right? Or again, you could just count the squares. That's probably the easiest way to go about it in this case. Third diagram, notice the base length is 3, and then if we count the squares, we're going to have 10 squares. So that's going to be the area, and then the base length here is 4, and then the amount of squares is going to be what, 17, like that. And that's all the diagrams that we have that we can use to make this table over here. So now we have this table. So notice that we have an independent variable, a dependent variable. So when we're calculating the finite differences, we're using the dependent variable. First off, we have to make sure that the independent variable has the constant spaces between them. We've gone through that when we've gone through finite differences in a previous video. And notice that it does, right? It's all going up by 1. So we could take the differences of these values here, of the dependent variable values, or the y values, quote unquote. Once we make our equation, I'll probably just use a, right, to represent the area, but if you want, you could use y and x. You can use whatever letters you want. So calculating the finite differences, remember, it's the bottom minus the top. So over here, we'll do 5 minus 2, which is 3. Then we'll do 10 minus 5, which is 5. And then we'll do 17 minus 10, which would give us 7. So notice that the first difference is they are not constant, so we're not dealing with a linear relation. Let's take the second differences, same thing, bottom minus top. 5 minus 3 gives us 2. 7 minus 5 gives us 2 as well. Right, so we only have two constant differences here. Usually I recommend having more, but in this case, unfortunately, we can't get more because there's no other points that we are given in the table, no other diagrams. So we have to go with these being constant, and therefore, because the second differences are constant, we are dealing with a quadratic relation. All right, so that is part A. Now, what about part B? What we have to do is now come up with an equation. Okay, so a couple of different ways to do this. So let's go back to naming these. So I'm going to let the A be the area, and then the base length, let's just let it be x, like that. Okay, so because we're dealing with a quadratic, we know that we're going to have something in the ax squared plus bx plus c form, like that. And different ways you can go about this. So you can, we've done this before, you could pick 3 points, plug them in for the x and for the capital A, and then you could solve for a, b, and c using substitution or elimination. Another thing you can do is look at the pattern and then try to come up with the formula yourself, just intuitively. And notice that in this case, a lot of times you'll be given like fairly complex diagrams, and so coming up with the pattern might be a little bit more difficult. But in this case, I feel like we can do it because notice that, let's write out these base lengths over here. So we have a base length of 1, 2, 3, and then 4. So notice that what's happening is that the area, we're multiplying by that same base length. So notice here we'll have 1 times 1, 2 times 2, which would give us these 4, 3 times 3, which would give us these 9, 4 times 4, which would give us this 16. But then there's always this one other square at the top. So if you think about it, what we're doing here is, if you want to break this down into a formula, you can kind of tell that what we're doing is we're, again, multiplying this by itself. So we're taking the 1 squared, but then there's always this other square up top. So then we're adding 1. Notice here, we're doing 2 squared, which would give us this 4 over here. And then we're adding that 1 square at the top. Over here, notice we got 3 squared. And then we're adding that 1 at the top. Over here, we got 16, which is 4 times 4, so we'll have 4 squared, and then we're adding that 1 at the top, right? And then notice if you do these calculations, you end up with these values over here. Okay, so that's another way to do it. You could kind of just visually look at it and then try to intuitively go about it. Okay, it's not always going to work. Sometimes the diagrams or the patterns are fairly complex, and then you have to just do it the longer manual way of finding the A, B, and C using 3 points. And even in this question, you could take 3 points if you want, and you can do that process. And what you should end up with, notice that if we generalize this, so if we keep going, right, if we have like a 5 over here, this is going to be 5 squared plus 1. Well, what if we have an x, just any value, whether it's 10, 100? Well, it's going to be x squared plus 1. And so that is the formula that relates the base length to the area. So what we could say is the area equals x squared plus 1. Okay, and we just came up with that looking at the diagrams. Now, if you do it that longer way, where you're finding the A, B, and C values, then what you'd end up getting, the values you'd end up getting is A is 1, right? Notice there's like a 1 in front. The B is 0. Notice that there's no BX term here. And then the C would be 1 as well, right? The C value is that right there. Right? So if you did it that way, and we've gone through a couple of videos doing that, so I'm not going to go through it here because it would take a little bit of time, but if you do want to practice that right? Plugging in these values. So you'd have to, again, come up with 3 equations like we've done before and then solve for that A, B, and C using substitution or elimination. These are the values you should come up with. And so you'd end up with that same formula. But in this case, again, the diagram wasn't too bad. So we just kind of came up with the formula looking at it intuitively. Right? So that is the formula, the quadratic formula that relates the area A to the base length x. Right? And you could test it. If you plugged in all of these, you'd end up getting these particular areas. Okay, and then finally, it's asking us what are the transformations that are done on the base function x squared. Well, we have x squared, and then we have x squared plus 1 over here. So notice that if we look at it from the vertex form, which is how we usually look at transformations, right? Just be careful here. This is a different format than this over here, right? But this here, we can rewrite this as well as basically x minus 0 squared plus 1. There's like a 1 in front, right? This and this are the same. So notice that if we're getting the transformation values, what's the a value? It's 1. What's the h value? It's 0. What's the k value? It is 1. A value of 1, we know there's no transformation. H value is 0. It's not shifted left or right. K value of 1 means it's just shifted up by 1 unit. So that's the transformation to go from here to here. All right, so the transformation is there's a translation or a shift 1 unit up. All right. So fairly simple in terms of stating the transformations, right? It's just in that x squared plus k format that we've gone through in previous videos. The more challenging part is creating this table and then coming up with that equation.